welcome to this explainer. Today, we're diving straight into an incredibly fascinating 80-year-old math cold case. We're going to look at how, in May 2026, a general-purpose AI reasoning model completely upended what we thought we knew about geometry. Now, we aren't just going to look at the final result here. We're going to break down exactly what the problem was, why the absolute best mathematical minds in the world couldn't solve it, and how an AI used a, frankly, shocking burst of creative reasoning to finally crack it wide open. Here is our roadmap for today. First, the 80-year dot puzzle. Second, the impossible math gap. Third, how AI broke the rules. And finally, the future of AI math.
Starting with Section 1, the 80-year dot puzzle, deceptively simple geometry.
So, our cold case is famously known as the unit distance problem. It was first posed by the legendary mathematician Paul Erdős way back in 1946. And the thing is, it asks a deceptively simple, highly visual question. Basically, if you place a certain number of dots, let's call that n dots, on a perfectly flat piece of paper, what is the absolute largest possible count of dot pairs that are exactly 1 unit apart from each other? I mean, it sounds like a middle school puzzle, right? But mathematically speaking, it is an absolute beast. Now, if you want to maximize these unit distances, your very first instinct might be to just line the dots up perfectly straight, equally spaced apart. But doing that with n points only yields n-1 unit distances. Mathematicians call this linear growth. It's a start, for sure, but we can definitely do better than a straight line. If you take those same exact points and arrange them in a square grid, kind of like graph paper, you suddenly unlock horizontal and vertical neighbors. This gives you significantly more unit distances. And honestly, for decades, experts firmly believed that this clever little graph paper trick was essentially the absolute optimal strategy you could use. Moving to Section 2, the impossible math gap, a decades-long roadblock. For 80 frustrating years, some of the world's brightest mathematical minds were completely, helplessly stuck on this. They were trying to rigorously prove the exact upper limit of this geometric growth. But the math, it just simply refused to cooperate. The mathematical reality they were facing was totally mismatched. On one side, you had experts guessing that the upper limit was near linear growth, meaning slightly bigger than a straight line, but really not by much. But the best actual proofs human mathematicians could muster topped out at a massively divergent ceiling. The math just wasn't mathing. The conjectured or guessed answer was super low, but the proven ceiling was sky high. There was this giant, unbridgeable theoretical gap. Which brings us to Section 3, how AI broke the rules, a deep algebraic leap. Okay, so May 20, 2026. This is when an open AI reasoning model stepped up to the plate and brought a totally mind-bending weapon to a geometry fight. It didn't just crunch grid numbers faster, and it didn't just draw a bigger piece of graph paper. It generated an entirely new, infinite family of point configurations that completely shattered that 80-year-old prediction. And here is the knockout punch. The AI proved that the unit distance growth is genuinely polynomially better than expected. Instead of a shrinking exponent, it proved a fixed delta that is greater than 0. Now, later on, a human mathematician named Will Savin actually refined the AI's proof, and he pinpointed that delta at 0.014, meaning the lower bound of unit distances is actually roughly n to the power of 1.014. Just like that, the 80-year-old conjecture was officially dead. But how? This is where the story gets incredibly cool. The AI achieved this by completely abandoning simple visual geometry. Actually, scratch that. It didn't just abandon it. It totally translated the problem of dots on a page into the realm of deep, abstract algebraic number theory. It realized that counting equal lengths on a physical page is mathematically similar to counting the many ways you can represent a number arithmetically. So the AI built high-degree number fields. It used what mathematicians call split primes to simulate a bunch of different unit-length directions. It then used a class group pigeonhole argument to control these elements. If that all sounds insanely complex, well, it is. Essentially, the AI translated flat dots into a hyperdimensional alien language that seemingly had absolutely nothing to do with basic geometry. But here is the real magic trick. For that final step, the AI mathematically projected those abstract high-dimensional arithmetic objects perfectly back down onto our flat, ordinary 2D Euclidean plane. It's like it built a multidimensional mathematical skyscraper, found the exact answer at the very top floor, and then cast a perfect, flawless shadow of that answer back down onto our 2D piece of paper. Section 4. The future of AI math. Collaborators not calculators.
So, what does this monumental achievement actually mean for us? You might be wondering, did this general purpose AI just solve all of geometry in one swift move? Like, should we all just pack up our protractors and go home? While the reality is highly nuanced. While the AI brilliantly disproved the 80-year-old Erdős conjecture, and it definitively proved that basic grids are not optimal, the mystery isn't entirely over. The exact absolute maximum number of unit distances, that final ceiling we talked about, still remains an open, unsolved mystery today.
As the source material carefully points out, the real milestone here isn't that AI solved everything. The accurate takeaway is that it successfully took down a specific, highly central mathematical roadblock that had literally frustrated humans for generations. This firmly establishes AI in a brand new light. We're seeing that it is no longer just a calculator or a tool for checking human code. It's a creative collaborator. It's capable of generating entirely new research-level ideas. The AI had the creative insight to map a geometry problem to abstract algebra, while human mathematicians like Will Sawin stepped in afterward to verify, refine, and really contextualize those proofs. It's a true partnership now.
And this leaves us with a thrilling final thought to ponder as we wrap up. If a general-purpose AI can bridge an impossible gap in a decades-old cold case by looking at the problem through a completely alien lens, what other supposedly unsolvable problems in physics or medicine or climate science are about to crack wide open? Thank you so much for joining me on this explainer. Keep questioning, keep learning, and I'll catch you in the next one.